Hi, I'm Larry CRUM, and I'm going to talk about a field that I've been working in for 45 years, maybe, something like that, and it's called cavitation. And then I'm going to show how cavitation has some applications in the field of medicine. So what is cavitation? Maybe 100 years ago, people found that the propellers on ships were eroded very rapidly, and the ships could not go very fast because the cavitation, it turns out, eroded those propellers. And the reason for that is as the flow went past the propeller, it generated cavities on the surface of the propeller, and those cavities generated holes in the propeller itself. And these were bubbles that collapsed and formed jets in the side of the propeller. And those jets were formed from bubbles that grew and collapsed. And also they emitted shock waves. So cavitation, in a sense, is anything to do with the growth and collapse of a bubble in a liquid. And there are various variations of that throughout the field of physics. Now, why do we have a bubble that collapses? If you think about the fact that a bubble in a liquid cannot exist in equilibrium because of surface tension, the so-called Laplace pressure. So the Laplace pressure, 2 sigma over r, means that the surface tension is going to drive the gas out of the inside of the bubble. And so bubbles do not exist freely in a liquid. They all collapse. So there must be a stabilization mechanism. So big bubbles will rise out of the liquid, small bubbles will dissolve because of surface tension. So there has to be what we call a cavitation nucleus. And over many, many years, we've developed this sort of crevice model of cavitation. And in this particular case, particles in the liquid with cracks and crevices in them can stabilize gas. And then when the pressure is reduced, then the air comes out of these crevices, and we call this nucleation. Of course, there are also cases in which bubbles are actually stabilized by surface active membranes, but this is only under special circumstances. So bubbles act as nucleation sites, but the bubbles have to be stabilized some way or other. And we call this diffusion stability. A bubble in a liquid driven by an acoustic field can be treated as force equals mass times acceleration. But in order to do this in detail, one has to account for all of the internal pressures, the external pressures, and so forth. And so Rayleigh was one of the first to develop an equation that describes the motion of a bubble in a sound field. And this is kind of a complicated equation here, but nonetheless, and there are lots of modifications of this. But this equation works quite well if you add all of the terms and so forth. And so let's just examine what happens when you have an acoustic field that varies in time and a gas bubble of, say, 1 unit in size. So when the pressure goes negative, then the bubble must grow. And when the pressure goes positive, this bubble filled with vapor, because it's growing to many times its original size, collapses. And that generates shock waves and perhaps liquid jets. And one can show that actually the temperatures inside the bubble on just an ordinary, this particular pressure, for example, the pressures can be millibar or megabars and kilobars probably, and the temperature can be up to 7,000 degrees. That's the temperature of the surface of the sun. So what bubbles do is concentrate the acoustic field energy into a very small spot. And this concentration of energy is what gives cavitation this very important quality. So if you were to measure a bubble and use the equations describing cavitation, you see you have a very good description of it theoretically. So if one is talking about a single bubble, one can model a single bubble quite accurately by the equations of cavitation dynamics. Now here is a movie of a bubble, and you can compare sort of in your mind the growth of the bubble, the few bounces and so forth. So you see this single bubble driven by an acoustic field is pretty well characterized by the Rayleigh-Plesset equation modified to include additional terms. An interesting thing about a bubble collapsing like that, even though it can generate high temperatures and high pressures, the bubble is quite small. So if one were to calculate the energy in the bubble itself when it collapses, it's quite small. It's on the order of nanojoules or MeV. So if you think about nanojoules, that's very small, but MeV, million electron volts, is quite high because 1 electron volt generates essentially a temperature of 11,000 degrees. So in a sense, on a molecular level, the temperature and the energy is very high. On a macroscopic level, it's quite small. For example, ionization energy to break molecules apart is on the order of a few MeV. And we have available here MeV. So people have actually supposed that if you had bubbles collapsing and generating 100 MeV, you could get close to the actual fusion, a deuterium-tritium fusion. This is kind of extrapolations and so forth, but people have actually sort of suggested that bubble collapsing could actually result in DT fusion. And the reason for this is that there are single bubbles that can be levitated in an acoustic field, and this movie shows that the bubble levitated in the field, that's that little white thing in the middle of the wine glass that is darting back and forth, and that is emitting light. And the light that's emitted can be measured on the order of tens of electron volts, maybe even hundreds of electron volts. Not necessarily MeV, because not all the energy of the collapse is given into the energy of the bubble itself. So this concept of single bubble sonoluminescence has given us a very interesting way to find out the energy concentration by the acoustic field. So let's apply some of these ideas to medicine now. When we have this bubble collapsing, it can collapse with such violence that it destroys itself in one cycle. Or it can collapse at a lot less violently, and the integrity of the bubble remains from cycle to cycle. If the integrity of the bubble remains from cycle to cycle, we call that stable cavitation. If it destroys itself in one cycle, we call that stable cavitation. So here's a case where bubbles were introduced or in a millipore filter. So there are holes in this millipore filter, and those holes are filled with gas, and then an acoustic field is applied, and you see the bubble, if this is a pulsating field, causes acoustic streaming around the outside, and the red blood cells in this streaming field are sheared, and one can see here that you can actually cause clotting. So in a sense, this is a direct application of a medical or a biological effect of stable cavitation. So stable cavitation is a single bubble that remains in its sort of integrity through the acoustic field, and this oscillation can have biological effects. One of the reasons why a bubble stationary near a surface driven by an acoustic field is that it develops what we call cavitation microstreaming. And here is an example. If the bubble is oscillating, then of course the liquid can't come in from the bottom because it's on a surface. And so as the liquid comes in, as the bubble gets smaller and goes back out, you get this streaming. And in the surface here where it's going go very fast, then you get shear forces that can tear apart membranes, and so you can see that this is a way to have a biological effect. If there are, as this bubble oscillates, you can get surface waves on the bubble, and you can get subharmonic emissions. Now, we'll talk about that later, and that's a way to measure stable cavitation, the emission of subharmonic emissions. Now, a particular prototypical example of the application of cavitation in the field of medicine is extracorporeal shockwave lithotripsy. So in this particular case, you have in the original Dornier human machine, the HM3, a shockwave is generated. This causes a collapsing shockwave on a stone in the middle of the kidney. This is extracorporeal, and the shockwave looks something like this, with a very rapid rise time. These rise times are very difficult to measure. Pressures going up to 30, 40, maybe even 50 or 100 kilobar, and or megapascals. But then following the leading front of the shockwave is a very relatively deep trough, and this is a negative pressure. This negative pressure gives rise to cavitation. Whenever the pressure drops below the atmospheric pressure, one can get a bubble to grow. And so in this particular slide here, we're shooting the shock waves at a kidney stone that is held in this particular position here near the shockwave focus. And this movie shows that this one shockwave develops this huge cloud of bubbles, and the cloud collapses in a very violent way on the surface of the stone. And this collapsing shockwave and liquid jet can result in destruction of the kidney stone. So there are shock waves that are generated by the lithotripter. They themselves can cause the stone to break up, but the cavitation is also a mechanism for stone comminution or stone breakup. Lithotripters come in many sizes. At one time, 80% of kidney stones were treated with lithotripters. Now the new designs aren't as efficient as the old ones, and so they aren't as successful. But a lithotripter focus on a stone will cause the stone to break up into little pieces. And if it breaks up into little pieces, then the body can pass these small pieces just naturally. Here's a movie of a stone, a kidney stone. It's a synthetic kidney stones in a liquid, and now you're going to see the action of the shock wave. Let me back this up and show it again. You see, every time the shock wave hits it, it moves the stone a little bit, and as these shock waves hit the stone and generate cavitation, you can see the stone is being broken up. And after about 100 shock waves, not very long from now, the stone is broken up into smaller pieces. And then after 3000, which is sort of the company recommended treatment, you get quite small stones. It's important to recognize that it is cavitation in this sort of polarity, that is, if you have the positive pressure first and the negative pressure second, that allows these bubbles to grow. Interestingly enough, if you reverse the polarity, which you can do by reflecting off a pressure release surface, and have the negative pressure first and the positive pressure after that, this polarity will not break up a stone at all. And in fact, it won't even do a single thing to the stone. And so that implies that cavitation is a very important criterion or mechanism for stone comminution. One of the important things in generating cavitation in a biological medium, human body or something like that, is to know when you have cavitation. So we have developed over the years things called passive cavitation detection. So in this particular case, the shock wave is focused at a particular time or in place, and cavitation occurs, let's say, at the focus. Then if you have a transducer that is listening, in a sense, in a passive mode, it can see or measure the shock waves that come out. And so if you were to calculate what happens to the bubble, the initial positive pressure causes the bubble to collapse, the negative pressure causes the bubble to grow, and then it collapses. And you would calculate that you would have a little bit of sound emitted here and a lot of sound there. And here is a measurement of a PCD, which showing that you get some sound emitted, as you had predicted, and a lot of sound emitted later, which you can measure. So passive cavitation detection is necessary whenever you have a cavitation possibility in a biological system, so that you know if you have cavitation or not. Here is an example of a passive cavitation detector in the sense that we have two transducers, focused transducers, that are focused at a particular point, and they are listening, so to speak, for the cavitation produced in a particular system. And so in this particular case, there is an imaging system that can look at the tissue, of course, diagnostic ultrasound, and then we have these two passive cavitation detectors that are passively listening. This system can, the diagnostic ultrasound system can actively look at it. These listening transducers are passive detection. And here's a movie that shows the kidney in a pig, and now the shock waves coming in. Let's back that up and do it again. The shock waves coming in, you see that artifact coming in, and then you see these hypoechogenic echoes coming off of this. This is the active cavitation system seeing the scattering from the bubble clouds that are generated by cavitation.